Two things before I can finish up with this one. I don't think this is going to take too long. One, when you finish up this chapter, go ahead. I'm not going to lecture over it, but go ahead and read this polycyclic systems. That's pretty interesting, I think. And talks about steroids. And there are medications that are steroids. I've had them before. Usually there's anti-inflammatories before or after a surgery to study the effects of the surgery, for example, is one application of it. So read that when you're done. Now, back on 435, and sometimes you're saying something you know it's not right, but it's like you can't help yourself. I was saying something about 4.35b, which was compound A or compound B. And I was talking about one is a chair, one is a twist boat, and I misspoke. I didn't say this right. When you were looking at compound A and B, B was the one that goes into twist boat. I made it sound like this tert-butyl group could swap places with the hydrogen in there. And I even drew that on here. But that can't happen once the molecule is made. What's going to happen is when the molecule is being made, that this isomer is not favored, so will not be made, whereas this isomer will be the one that's made. Okay, but what it doesn't do is it doesn't switch positions once it's made. Okay, I like the way that sounded. That came out about right. And that comes into play here on one of these that we're talking about on the next section. So we start with 4.36. We were talking about cis-trans stereoisomerism. Okay, it says draw the Hayworth projection, that's this guy, for cis-dimethyl cyclohexane. So it should look like this. It's two methyl groups. It's a cyclohexane with two methyls off. They're cis, so they're both up, and they're in the 1 and 3 positions. I'm going to call this one the 1 and this one the 3, or you could do it the other way around and get the different result, the same result a different way. Now when I draw this, and I draw it up, then my bow tie here, I've got a methyl group up. Go ahead and draw the hydrogens in there, and that's going to be equatorial, whereas the methyl group is axial. And then at the third position, you got methyl group up, which in this case is axial, and hydrogen is equatorial. Now, there would be a lot of stereo interference between those two. And I want to remember to say something when I get here to compare these two. So if you flip this down, and this actually can happen, this can flip down into the other chair configuration, then this methyl group would be out here, this methyl group would be equatorial. They would both be equatorial. Obviously, this is a preferred lowest energy. Well, once you know what's doing this is obviously, because this is what, 7.6 and 7.6, and this is next to 0 and 0. All right, so let's try the trans. Now, it's very important to realize you can't flip the cis stereoisomer and make it into trans. One of these would be highly preferred, probably, upon synthesis. And the other one would be highly excluded, for lack of a better word, upon synthesis when you're making it. So if you have your methyl groups in the 1 and 3 position, let's draw those two chair conformations. And this is the Hayworth projection, and the lines are thicker in front to show that they're closer to you, and that's farther back. So methyl up, methyl down. Methyl up here is axial with a hydrogen in the equatorial position. In the third position, I drew this wrong initially, but the methyl group should be down, which is equatorial, and the hydrogen should be axial. It's messy because I had it backwards at first. Okay, and when this flips down, and this flips up, and that flips down, this methyl group would go to equatorial with a hydrogen axial, and this would go to methyl axial hydrogen equatorial. And this one is 7.6 with interference here, steric interference here. This one is 7.6 with steric interference here. Both of these are about 7.6. So when you're making this 1,3-dimethyl cyclohexane and there's some reaction conditions, the one that's going to be favored heavily is not trans, because these are 7.6, but cis. And when it's made, it will take this chair conformation because that's next to 0. Okay? Now, we're going to talk about this one and come back. If you do from problem 4.37, the problem is cis 1,4-dimethyl cyclohexane. So it's another isomer. The difference is when you draw your Hayworth projection here with the heavy line, the one closest to you, our methyl groups are on opposite ends of this molecule. So what I had before was, let's see, this one, where I was either trans, here's my methyl groups, trans, I think, yeah, or cis. So what I had before was this. And the one that's most preferred is, let's see, I've got there's my chair. What did I do wrong? Anything? Yeah, this is the one I have on the left. They're both sterically interfering up here. The one that's preferred is this one. I did something wrong. What did I do? Not flip this down. Oh, this one. Yeah, this is the one that's preferred. I had the preferred one at first. I didn't realize it. Okay, what is not preferred is this one. There we go. Now you can see that really heavy interference here. That's just not going to happen. Okay, so let me now go to this one. So I'm going to move my methyl group here over one. I'll move it over here. And what I've got is, if I can put it together, let's see, here's cis like so. Yeah, that's just not going to happen. But that is not the same as what I just did. One of the things I was going to point out is I could work cis for these two and get 15.2 up for these two. And I guess this would be trans here. Okay, well, before I get that far, I was going to discuss that, but I wasn't ready to discuss that. All right, let's go here. So I have a cis up, cis like so. Now, we have two chair conformation. That's not going to, we're not going to want to do that one. But what about this one? Well, it's kind of the same thing. Either this is up first, and that's down, or this is up, and this is down. It's the same thing, but backwards. In this case, you could flip it around. It's the same thing. Be careful with that, though. Okay, so I have an up for my methyl, axial, hydrogen and equatorial go around to the fourth position. My CH3 is up and axial is in equatorial. My axial position is H. If I flip this side down and this side up, my CH3 goes to equatorial, my H goes to axial, and over here my CH3 goes to axial, up, and H is equatorial. And those are the two that are the same. So these are both as 7.6 at cis. Now, if I go back to the previous example, it was trans that was 7.6 for both of them. But here's the thing. That's 7.6 on both of these, and this 7.6 for both of these is not going to be exactly the same thing. They're going to be a little bit different if you could run the software on there. Let's look at the trans. You might see what's coming here because what happened before. So let me flip that around. These cannot happen. These cannot flip on their own. I accidentally said that on the last, that's what I was correcting at the beginning. If I put, what happens is when they are synthesized, there's a high preference for one way versus another. But once they're made, they don't flip. So this one can either look like so, or flip this side up and this side down, like so. Okay, there's a lot of interference here, and there's a lot of interference here. We'll see that. So I can have my CH3 up in the axial position, hydrogen equatorial, go around 4, 1, 2, 3, 4. Here I have CH3 down, hydrogen in the axial, hydrogen equatorial. So that's what I have here. Lots of interference, lots of interference. That's going to be a 15.2. How do I get 15.2 on that? Oh, because it's 7.6 apiece. The other way, if I flip this one down and this one up, this doesn't work very well. This one didn't go down. There we go. Now they're both sticking out there in equatorial, and there's very little interaction. So those are approximately 0. So what's preferred? Well, when you go to make it, 0 is preferred over 7.6. And this is the one that's going to exist at. So it says, determine whether the cis isomer or trans is more stable. Trans is, but more specifically, this version of the trans is. Okay? This chair conformation of the trans is most preferred. Okay, then it gets a little more complicated. And I'm not going to do this one with a model because I'll have pieces everywhere. But it wants to know on this one the same thing. We've got a trans 1,3 di. Oh, I forgot my di. Cis 1,3 di tert butyl cyclohexane. So there's a tert butyl, there's another tert butyl, and they're cis to one another. They're this way, and they're in the 1 and 3 positions. And this is closer, that's farther away. All right, so let's draw that one. So if I make this my 1 and my 3, the 1 is up in the axial position with the hydrogen equatorial, and the other one is up axial, hydrogen equatorial. That's going to have huge interference. In fact, it's 22.8 doubled to 45.6. This one with them sticking out is about 0. If you flip this one down and go to equatorial, flip this one down and go to equatorial, there's hardly any interference. So this is going to be highly preferred. Okay. And the other one is going to be primarily in a twist boat. So let's talk about trans. Here it is. So if I do my two chairs for this, we go up, hydrogen is equatorial. This one is down, hydrogen is axial. That's a 22.8 interference there, whereas this one's sticking out. It's not bad. This one, if we flip it down, I ran out of page here because I drew this too big, but that's sticking out there equatorial, so it's not hurting anything. But this one went down into an axial position, and it's 22.8. So what's going to happen is this will go to twist boat. It'll, see if I can draw this. This is supposed to be close to you. This is supposed to be farther back. And I'd have an equatorial here. This one's sticking out. And this one here would kind of stick out this way. That's okay because when this is down here, I don't have this one built on a model, but when this is down here, it's closer to the bottom. If you go to a twist boat, this tert actually slides out here a little bit more and kind of sticks away. You can see the angle isn't straight down now, it's out this way. And now it's kind of out of the way. So that's why it works that way.